Hey guys, welcome back to the How to Implement the FFT for Audio Programmers tutorial series, and this is part 4 where we're going to optimize the previously made recursive FFT function. If you haven't seen the first 3 parts, please watch them. This is meant to be watched as a series. Everything builds up. You'll see how we construct the FFT algorithm, where we come from, and then how it works, and please just watch it. But if you have, then let's go ahead and start implementing this or optimizing our current FFT. So just where we left off last time, we have this recursive function of FFT, and it uses our method of taking the evens of evens and odds of odds and going down until we perform what's called the 2-point discrete Fourier transform. Hopefully this is a little bit easier to see now. But basically we just took this from our previous function where we solved for one particular bin, and instead we just solved for every bin. Additionally, we solved for 2 bins at one time because with our even and odd values, we only have the length over 2 for each of them. So what we realized is that because of trigonometry or just basic knowledge of how graphs work, or particularly on a circle, right? When you take the point opposite on a circle, you have, if you want to get the opposite side of that circle, it's just negative x, negative y, that's the point. That's how you get there. And so basically we just applied that here. We still followed the formula with the even, but instead we actually subtract the odd value, and this is put into the bin that is above length over 2. So the other point of the circle, you could think. So anyways, we have this, and we can see that it works over here. We didn't implement the inverse fast Fourier transform yet, but that's okay. So what are we going to try and do? We're going to try and implement the in place FFT first. So that's kind of daunting, right? It seems kind of crazy. I'll go ahead and just make this function. It's also going to take coefficients. So let's just plan out what we want to do. And before we plan out what we want to do, let's take a look at what the recursive function is really doing. This details exactly what is happening in our recursive function. So basically we start out with our bins, and these are the bin numbers. And we start out with these. And then we take the evens and odds of these, put them into 2 groups, even and odds. And then we again take the evens and odds, right? So as you can see, I've colored these things appropriately, right? We take 0 and 4, those are the evens of this group, and we put them here. And then we take 2 and 6, those are the odds of this group. So this is the evens. This is the evens of the evens and the odds of the evens. And rightly so here. And notice 3, 7 is the odds of the odds. Also notice that 0 always remains the most even number, and I guess you could say 7 remains the most odd number. It always stays in their positions. So basically we keep doing this, right, until we have as far down as 2 components, and that's when we start going back up the recursive chain, and we take 2-point discrete Fourier transforms all the way back up. So we do it once with terms, the most evens and the most odds, etc. Then we go up a stage and we do it again, and notice that this aligns with this stage here. And finally we do the 2-point discrete Fourier transforms with the original order of whatever is in the bins, and then we have our result, right? So a closer look at this, I have a chart on the right here, and this is what's called a butterfly graph, and I guess it looks like butterflies to some people, not to me. But basically this shows in detail what happens when we don't consider by bin, instead we consider by position, right? So if we think of these as array indices. And so what happens here is we start out by doing what we see on the left, almost exactly the same, right? This is a 2-point discrete Fourier transform. These are equivalent, right? And if you want to know what that means, this is our rotation by omega, which we do here. This is the odds value times cosine minus odds value times sine. Right? That's all that means. This is adding input, right? This is why the evens are added to both. As we can see, we have evens value here and even value here. And note that these are two separate points, right? This is the even and this is the odd. So then that's what subtraction means here, because when we assign this to the odd position, we are subtracting the same thing that we added originally, which is the odd value, right? So that's all this means. It's just kind of a visual way of understanding that. Now notice that when we go to the next stage, we actually stretch out. And note that we're doing it, these points align, or the discrete Fourier transforms align with the left graph here. So you see 0 and 2 are being done, that's a 2-point transform. I know it gets a little messy, but the point is that this is exactly the same on the left and right, but on the right we see how to do it based on positions instead of by bin, which is going to be useful in our in-place implementation. And then finally in the last stage, it's just 0 with 1, right, 4 with 5, 2 with 3, and 6 with 7, etc. This is the same thing as the last thing on the left, and then once we have that, we also have our result. So these align. These are essentially the same thing. Now some important things to take note of, we have the separation, I'm calling them. That is basically this distance here, right, the distance between the groups, and first it is 2 to the stage, right? This is stage 1, if we think about it like that. The separation is 2 to the power of stage, because it's 2, and then we have our next group, and then 2, and then our next group. And then in the next one, right, this is stage 2, so this is 2 to the power of 4, so separation is 4, right? This is the total number of elements per group, you can also think about it. And then, so you have 4, and then you have another 4, right? And then finally, this is stage 3, so this is 8. And so this is the total length of the group, which is actually equal to the length of the input, right? Now the width is basically just, in my terms, the distance between the points that we're doing the 2-point discrete Fourier transform with. And that's going to be equal to the separation divided by 2, right? So 0, 4, this distance is 1 right here, right? 0 and 2, this distance is 1, right? 0 and 1, this distance is 4. And so that is just equal to the separation over 2. And note that this is also equal to the number of evens and odds per group. When we implement this, we have to keep going down the line, right? 0, 4, 2, 6. And that's how we know, we just keep going down the line. That's how we know how many times we have to do that, right? Okay, so hopefully that makes sense. Feel free to just kind of let this soak in, pause the video and just figure out how these are equal, what exactly we're doing. But this right chart is really, really helpful because this is exactly what our elements are going to look like in the arrays, if you use some imagination. So just remember this, and we will refer to this when we start our implementation, right? So now that we know the general theory behind how this works, I'm just going to do some pseudocode, or rather just comments. So the first thing we have to do is rearrange our elements in even, odd, recursive order. Right, and then at that point we'll be down here, and then we have to do 2-point DFTs for log n stages. So then we have to perform 2-point DFTs for log 2 n stages. Right? Okay. And then this is just basically where we take note of separation of width. That's where this is implemented. Okay. So now let's attack the first problem of rearranging the elements in even odd recursive order. How do we even attempt this, right? How can we like programmatically figure out the most even and odd arrangements? Well, if you notice, I included the actual bit representations of these numbers with log 2 of n digits, as you can see, because we have 8 elements here, and log 2 of 8 is 3, and so I have 3 bits. And if you're clever, you'll see that we have bit reversed every element at the bottom from the top. So we start with the top, we get to the bottom. How do we get there? We actually bit reverse all of the elements. You'll notice numbers like 2 stay the same in this particular case, right? But it's important to note that we bit reverse with respect to the log base 2 of n, right? That's how we bit reverse. That's sort of the maximum or the highest bit. And so as you can see, they're all bit reversed. So I'm not sure who came up with this, but it may be Cooley and Tukey who just came up with the general FFT or applied FFT algorithm. So I'll give the credit to them. I'm not sure if they came up with it, but it's pretty neat how that works. But yeah, so that is basically our solution to part 1. So let's go ahead and just start with that and see where we get. So basically, what do we have to do? Well, I am going to actually change our DFT coefficients. All right, so I'm going to make them equal to the bin number that they will be in. And this is going to be really helpful. This will match our diagram exactly. All right. So we have updated our DFT coefficients. Now these are going to be different. This is in fact a discrete Fourier transform for these coefficients. Cool. All right, but now we know that we're going to be looking at the bin numbers when we do our swap. So that's going to be helpful just for debugging this particular function. Okay, so now we have to bit swap everything. So I'm going to make a variable called length, which is going to be equal to coefficients.length. I'm going to make a variable called log2, which is going to be equal to log2 of length. And then now I'm going to do a for loop. And this is going to be for rearranging all the elements. So that's for the entire length. All right. And so we're starting at 0. We're going through the length. We're doing all the elements. So we're going to have our new index. We're going to be 0. And we're going to just do this algorithm that I came up with. But it's not mine. I'm sure somebody else has done this. And it's probably one of the most popular ways of doing this. But basically what we're going to do is have another for loop. So j, and it's going to go through log 2, right? That's why the number of bits matters. We have to stop somewhere. And so this is how we know where to stop with our bit reversal. And then j++. All right. And so here's what we're going to do. We're going to say variable var, we're going to say match. And this is going to be equal to, I'll do this in a few stages. So what we're going to start with is considering bit masking. If you're familiar with bit masking, you'll know basically that means we take 1 and we bit shift it, and we just AND it with whatever we're looking at, and we see if the result is 0, because 1 ANDed with 1 is 1. 1 ANDed with 0 is 0. So that's how we know if a 1 is present there. And so what that means is we're going to start out at the lowest bit, which is 1. So I'm going to say 1 and bit shifted by j, right? And now ANDed with I. Right, so what does this tell us? Well, this either gives us 0 or the power of 2, which is 1 bit shifted by j, right? So in this particular case, that's 0 or some power of 2. Now, here's the thing. I'm going to do something that may not work in many languages. This is a simple check you can do, but I'm going to use 2 exclamation marks. And what this means is first it will negate, or sorry, not negate, but if it is not 0, it will turn it 0, and if it is 0, it'll turn it non-zero. But when you do 2 of them, it basically says, okay, if this is 0, this will result in 0. If it's non-zero, it will result in 1. So it's almost like a integer Boolean operator. I mean, it's a Boolean operator. But this will just basically either give us a 1 if there is a match there, or a 0 if there is not a match. Alright, so this is either 0 or 1 at this point. And so then what we'll do is we'll say new index is OR equal to, because we're going to OR it, and we're going to keep ORing it. And now here's the thing. It's going to be 1, right, bit shifted by what? We're going up by j. So we're going to say log 2. We're going to start from the top now, because we were approaching it from the low end. Now we're going to approach it from the high end, which is log 2 minus 1, actually, because if it was, in fact, log 2, it would be a step over, or a digit over. And so we're going to start by bit shifting 1 all the way over, and then we're going to subtract j. And so now when j is 0, and let's say we have a match at 1, it's going to bit shift 1 by log 2 minus 1, and that will be the highest position, and that will turn 1 into 8. Or, sorry, no it won't. It will turn 1 into 4, because 8 would be 1, 0, 0, 0. But we only have 3 digits, right? So this will turn 1 into 4, not 8. Alright, and if it's 0, you're just ORing 0 to something, well, it's going to be whatever it was before. So that should be fine. And now I'm just going to log whatever we get. So we do this, and I don't think I'm calling this function yet, so I need to go down. I'm going to keep calling that one, but then I'm also going to call this one. Alright, so as you can see, we get 7. So maybe this is not particularly a great way to do this in JavaScript. And so in fact, I think I messed up there. There we go. That's what I messed up on. I said 1, but it's really match, because that's what I meant about ORing 0. Anyway, my bad. Okay, so as you can see, now we match the elements, the top and the bottom match, right? 04261537, 04261537, because the bits have been reversed. All right, very cool, and not that bad. So now we actually need to, right, we have this new index, but now we need to swap the elements in there. So before we calculated the new index, and now we have to swap the elements, and now here's the catch. If I is less than or equal to new index, here's why. We're going to run into both of the indices twice, or once if it's the same, right? But if we run into them twice, right, like let's say we have 1 and 4. Well, if we have 1 and 4 and we swap them, well, when I get to 1, I swap it, but when I get to 4, I swap it again, so we end up not doing what we wanted to do, right? So now what we need to do is say only if I is less than or equal to new index, we're going to say we're going to have a temp variable, which is going to be coefficients of I. And then we're going to say coefficients of I is going to be equal to coefficients of new I. And coefficients of new I is equal to, did I not call it new I? I called it new index. Okay. All right. Cool. So now if I, after all this, this is coefficients. Let's see what our coefficients are. It's now 0, 4, 2, 6, 1, 5, 3, 7. Perfect. Okay, so this works, right? Great. That's 1/2 of the way done with the in-place FFT. All right. The next, right, is this whole part. But really, we should think about it as the right. Because the right is how we're going to implement it via code in place. Okay. So where do we begin? Well, we begin with our stages, right? So we're going to say it's a for loop, right? So it's for our stage is equal to 1. Stage is less than or equal to log 2. And stage plus plus, because we're incrementing the stage each time. Right, I'm starting at 1. You don't have to. You can start at 0 and do less than log 2. But because, as I showed you, separation is 2 to the power of stage, it just makes more sense to do it this way, in my opinion. Whoops. All right. Okay. So let me shrink this. Okay, so now what do we do? Right, we have all the information that we need to get from here, right? Separation is 2 to the power of stage. So separation is equal to 2 to the power of stage, and width is equal to separation divided by 2. All right, okay, cool. So, whoops. Now that we have these variables, what are we doing each time, right? It's a little bit obscure in the first stage, but basically what we do is we go through these things, right? So I mentioned that the number of evens and odds per group is equal to the width, because notice that we have to traverse through all those. But we also have to traverse through the groups, right? So I go through group 1 and then I'm on group 2. So that's why I actually did this with size 8, because you really get to see everything. And in this particular one, this shows you everything you need to know. So we're going to start out with group 1, and then we have group 2, right? So in other words, we know that the number of evens and odds, right, is going to be 2 here. And then once we do that, we can increment by the separation and then go to the next group, right? All right, cool. So let's do that. Let me just tell it to myself again so I don't mess up. So we start at group 1, right? And then we go through the offsets, and then we increment our starting point by the separation. Okay, I'll probably refer to that a couple times. So the next thing we do is another for loop. And this is going to be group 0, right? I'm using 0 indexing. And actually, let's see. This is going to be start. I'm going to call this start, right? Or start group, right? 0 start group is less than length, right? Start group plus, or sorry, plus or equal to separation. Right, that's what we're doing. Okay. Just cleaning up a little bit. So we're starting at 0, and then we're incrementing by separation, right? So that's what we'll do. We'll go through each group. We start here, and then we'll jump separation, which is 2 to the power stage, and stage 2 is 4, and then we'll move on. So that's what we'll do. And then in here, we'll say for our, I'm going to call this, let's see, I could call it offset, but let's just say even, I guess I'll just say even element, and that's going to be equal to start group. Even lm is let's see, how should I do this? So I started start group. Even lm is that seems like a lot of calculation, but I'll just do it for the sake of doing it. So even lm, instead of that, we should make this like a counter. So I'm going to just call this 0. And it's going to be less than what, right? It's going to be less than the number of evens and odds per group. So I'm going to make another variable and say var num evens, and that's going to be equal to width, as I mentioned. And so we're going to say less than num evens, and then even lm plus plus. All right? Okay, great. So now we basically do this num even times for each group, right? Okay, hopefully this works out to be right. So that's nice. So we're gonna have to base this, since this is not starting, since this is also starting from 0, we're gonna say, okay, let's see, bin is gonna be equal to, and I guess I should say what, even bin is equal to start group plus even element. And now this would say, like, for example, when they're both 0, okay, well that's going to be 0. And when it's 1, right, when even element is 1, it's going to be 4 here. And then we're going to jump over here, right, because we're plus or equal to separation. And then we're going to, it's going to be 1, right, because this even element is going to be 0, and then it's going to be added to start group, right, which is 4, and then for 5, it's going to be 1 plus 4. All right, so that's good. So we have the even bin, and then we have the start group plus the even element. And then from here, we can just say odd bin is going to be equal to what? It's going to be even bin, right, plus width, right? Because in this particular example, our width is what? Separation over 2. Well, separation is 2 to the power stage, so 4 in this particular one. And I'm doing most of my analysis on the second stage, by the way. Separation is 2 squared, which is 4, and the width is 4 over 2, which is 2. And so that's how we're going to get our odd element, right? So that's good. And then from here, we can do some calculations and just do our 2-point discrete Fourier transform, which we have already done a couple times now. I'm going to copy this and bring it down here, but we'll have to do quite a bit of changing. So because we're changing a value, right, that's already been made, we're going to have to create some values so that when we update particular values, they don't change our calculation. If something relies on something else, but I change that first thing, or the second thing, I guess, then we're going to run into an issue because that's not the value that I want, Okay, if that didn't make sense, I'll just basically, we're just going to pre-calculate values so that when we update the array, we are using the correct value, right? Because we don't want any dependencies screwing things up. Okay, so basically I have W here, omega, excuse me. I'm just doing bar. So now let's just calculate our even value. So, right, the real value, right, the real part of our evens is evens value of there, right? But really, it's just our even bin, so coefficients of even bin of 0, right? And then even imaginary is just the same thing, but index 1, right? So that's what even real and even imaginary are. Now, odd real is just going to be the calculation. So I'm just going to copy this part and paste this in here. And okay, let me scroll down. Hopefully I haven't been blocking that much. So right here, and we don't have this odds value. So we're going to use, actually, this is the important point. We're using coefficients, right? So this is an in-place thing, so we're just changing coefficients. So coefficients, not of I, of the odd index, right, or the odd bin, and then times cosine of omega, which also we need to go back and fix because this is really just going to be even bin, right, that we're working with. It's not going to be I, it's going to be even bin. And so then this is also, let's see, we've already got, no, this is good. Okay, so this is this, and then this is going to be index 1, which is going to be the imaginary component, not 11. Okay, good. And then odd imaginary is going to be similar, right? It's just plus, I could have copied the bottom one. But yeah, so that's pretty much it, odd real and odd imaginary. So now we don't need these anymore. I've effectively copied and updated them. What we're doing. And so now we just need to set the values in the array. So we know that coefficients of even bin, the real part of that is going to be equal to what? Well, it's going to be equal to even real, whoops, even real plus odd real. And then what? The imaginary part of the even bin, which is the first index, is going to be even real plus, or sorry, even imaginary, my bad, plus odd imaginary. Even with the naming conventions, I still screwed it up. Okay, and just a reminder that that's basically what this is saying. This is even real, and this is odd real, right? And this is even imaginary, and this is odd imaginary. So that's all this is saying. And then notice that when I did this with parentheses, that it's the same exact thing. So that's what we just did. We calculated this value. And so you can see it's even real minus odd real, and then even imaginary minus odd imaginary. And again, this is just because we need to keep whatever we have already, because we're, I guess you could maybe say recursively or iteratively summing up, right? We're still doing the DFT, right? We're summing, but we're summing what we already have. So that's why we start out with this positive even real and positive even imaginary. But we're now subtracting, right? We're doing that negative x and negative y thing, where this is Just the same thing, but negative x, negative y. So even imaginary. And then this is also just even, or sorry, odd, real, and odd imaginary. All right, and we need to change this is odd bin, right? And so what we've done just right here, right? This aligns perfectly, and actually I should include all this because this includes the actual DFT for odd real and odd imaginary. This is exactly what this means, right? We have the evens being positive for both, and then the odds being positive for the even, and then first we perform the rotation by omega, right? Or it's rotation by omega, but it's also just a DFT. And then we send that positively to the even, but we subtract it from our odd. So that's how that lines up visually to code. This is what this is doing, and we've done this many times before. And one last thing we need to do, this is our omega, right? And this changes based on the recursion. So coefficients.length, although we have it here, it's changing in the recursive function because the coefficient array is literally different size depending on the recursive stage it's in. But in this particular scenario, we need to make sure that we actually make it divided by the separation, because if you recall, the separation is also the size of the group. And so that should basically help make omega correct. And at this point, all we need to do now is return, and we're returning coefficients. Now, we don't even have to do that, right? If we just send coefficients as a parameter and we modify it, although we don't return it, it should still modify coefficients correctly. And now let's go ahead and see what we get. So here is the correct one that we've already had, and here is the in place one. And you can't really, because of floating point errors, see, let's see if I just make it bigger, it should be fine. And let's see if the points align, and let's see, we get basically 0 up top, again, floating point error. We get 9.65 and basically 4. So it looks like, guys, we have successfully implemented the in-place FFT, which is huge, because this in-place FFT is honestly, I wouldn't bother even optimizing the recursive one. And I say that, and now I kind of take it back. Maybe there's some use case I'm not aware of. But yeah, no, the in-place is always going to be good, especially for me as an audio programmer in C++. The in-place FFT is always the way to go. I think it just saves a lot of time. And so yeah, guys, we have actually just implemented an in-place FFT, which is really cool. This is honestly something you could probably use on the fly if you don't want to use a third party's FFT, like FFT for the win. I think that one, and then it's like FFT or the Wild West, one of those. Those are surely excellent. And magnitude's better, although I wouldn't say like significantly better, but they've been refined and they take advantage of particular things. Also, this is done in JavaScript, so it's like, I don't know, it's not a huge feat in JavaScript, because JavaScript is already so slow as an interpreted language. But anyways, yeah, this is pretty good news. We now have implemented the FFT in place. So at this point, I'm going to actually end the video because it took a little bit longer than I thought, but in the next video I will go over some optimizations of the in-place FFT algorithm, as well as just implement the inverse feature, which is not that complicated. We've already done it before. So yeah, thank you guys for watching. I hope you guys enjoyed learning, and yeah, stay tuned.